Okay, as I was saying, very brief recap on velocities and acceleration. First, let's have a quick look on what does it mean. What is the linear velocity of a link, of a point on a link that is rotating at a certain speed, at a certain angular velocity omega. Okay, so you tell me, this is point O, the fixed point, which is, well, the pinned point is O. Come on. And the point at which we want to know the velocity is P. So what is the velocity of this point? Imagine that this link here, this one, is a rigid body. So if it is a rigid body, the velocity of P can never be in the direction of the link. Do you agree? Because O is fixed, and if P moves away or closer to O, that means that the link is not rigid. So the only way to make this velocity possible is if this velocity is perpendicular to the link. So the velocity being perpendicular to the link means it can go in two directions. It can go in this direction, or it can go in this direction. So which one, given that omega is clockwise, which direction will P go?
The right.
Yeah, to the right. Why? I mean, because it's natural, so it's moving to the right. So at the next instant of time, let's say this time here, I'm expecting that P has moved along this arc of circle. All right. So now the instantaneous velocity of P is tangent to the circle. Now the circle is the trajectory that point will take. The velocity is always tangent to the trajectory. Why? Because ideally what you have to do is, remember, this is the position vector RPO at this instant of time. This is the position vector RP prime O, where this is P prime, at the next instant of time. We don't know when. We say next instant of time. So what is the velocity? What is the definition of velocity? Definition.
Displacement by time.
Displacement in time. So what do you mean? The displacement in time? How much displacement and how much time?
Well, the displacement is d theta times dr.
Okay, so what you want to say is that the velocity is basically the difference between the two positions. So final position minus initial position divided by the time interval. So it's final position minus initial position. So these are vectors. Okay, so let's call these vector, divided by the time interval, delta t. Agreed? Now, what happens? Well, let's say that this delta t is just a number, so it's a scalar, will not affect the direction of the vector, will just make it longer or shorter. Agreed? Agreed. So if we look at this difference, how do you take this vector minus this vector? This minus this. You have two vectors. So yeah, so the difference between two vectors is this. Do you agree with me? This is the velocity. This thing is RP prime O minus RPO. Agreed? Why? Because if I do RPO plus this, it gets me RP prime O. All right? So this plus this gives me this. So that is that this minus this is this. Agreed? Guys, raise your hand now if you don't understand, because this is fundamental. Okay, what happens now? This is, although this is an average velocity over this interval of time. That's the idea. What we want is to find the instantaneous velocity. Instantaneous velocity means when this delta t tends to 0. So if we take this over the limit for delta t going to 0, what do we get? Well, this is exactly the definition of derivative. Agreed?
Yeah.
This is dr over dt. That's the idea. And this is the derivative of a vector. Dr in dt, and this is v, which we can also say, if you look at this, this is d theta. Okay? So we can say that this arc here, this tiny thing, well, first of all, when we make delta t equal to 0, that means we are using a closer and closer vector. Okay? So we are going narrower and narrower and narrower until we are reaching the point where this vector here becomes this vector here, which is tangent, as I was saying. This one is the actual velocity of P. Okay? So you see, if you take a finite interval of time, it's not tangent. It's slightly tiny. So it's tangent only if you take the derivative, which is the instantaneous velocity. That's what we are talking about. And this, geometrically, this thing is just d theta times r divided by dt. Do you agree with me? Because this is d theta. So this arc here, this arc here is theta times r. Agreed? So d theta times r divided by dt. And that means that this is also equal to omega r. Because remember, what is omega? Omega is just d theta in dt. So I can call this omega, this thing. I call this omega. And so I get that the velocity of point P is omega cross r. Why do I use a cross? What is the cross product of two vectors?
Another vector.
Is a third vector that is perpendicular to both vectors and has direction given by your right-hand rule. Okay. So if I take omega, which is this vector here that goes inside the paper, omega is a vector that goes inside the screen as I've drawn it. Omega goes inside, and then I have to place omega, my hand, like this. I'm trying to. So you have omega inside, and then you have to put it onto r. Put inside onto r, you get this. And this is exactly the velocity of P. Agreed? Let me do this on the screen as well. Guys, I'm going to remove myself from the camera for a little bit because I want to show them the same thing. So what you have is that omega is inside, over r gives me this, and this is exactly dp. Right? That's how you do it. I'm back. Okay, so now that we know these things, we found everything. Well, this is the velocity of P with respect to a fixed point O. Agreed? What happens if O is moving? Well, if O is moving, we have to add the velocity of O to whatever is the velocity of P with respect to O. Okay? Because if O is going somewhere, P is following along the link and it's rotating around it. So the velocity of P, and guys, this is the formula that you need. The velocity of any point is equal to the velocity of a reference point plus omega cross. Let's use vector r PO. Okay? This is what you have to remember. This is the holy grail of the velocity diagrams. There you go. Use this every time you get all the velocity diagrams in your life, just with this simple formula. Can you please repeat that red equation? So this red equation here is the velocity of P is the velocity of O, so whatever O is doing, plus whatever is P doing around O. Okay, so imagine this here, we also call it VPO, which is the velocity of P with respect to O. And so we can say very easily, we can also say that VPO is also VP minus VO, because this is exactly the definition of relative acceleration. Remember what was relative acceleration? Is the velocity of a point minus the velocity of a reference point. That's what it is. And so I'm saying here with this blurb of thing here is I'm saying that the velocity of P, the absolute velocity of P is equal to the velocity of a reference point plus the velocity of P with respect to that reference point. Now, if the reference point is fixed, this is 0, and then we go back here. What I'm saying is that P is this point here on the link, and O is the fixed point on the link, or reference point. Okay? This is all you need. We can already start going here. And you have to have a bit of understanding of graphical analysis of vectors, because that's what you're being asked to do. So you know how to sum vectors graphically, you know how to subtract vector graphically, and you know which directions they take when you have these things. So I told you that VPO is perpendicular to both omega and RPO. Okay, this would be very, very, very important. Okay, so let's solve this one. Let's solve which one? This one. I'm not sure which one. We have 4, but let's solve this one because
the first one,
which is this. The problem is of this one, we don't do the velocity the acceleration diagrams afterwards. I want to solve this because of this one. We also do the acceleration diagram later. Okay. And then I'm going to solve this, and if there's time, I'll solve this one first. This one and this one. Okay. Okay, let's start. This is a mechanism of which we know we know complete geometric information. We know the geometry of this thing, although it doesn't look like we have that this is to scale. So we know, so this is 100 millimeters, however much this is. And so you can find the length of all these. Okay, so you have complete geometric information. You can't find it. You can't find the velocity diagram if you don't have complete geometric information. I mean, you can't find the actual values. You can see what's the shape, but you can't find the actual values. We also have that point O and point D are fixed to the ground there, and this structure is pinned onto them. So we have body 1 is the ground, as we love. We love to say that 1 is always the ground. And body 2 is this OA, link OA. Then body 3 is, of course, this entire triangle. So this triangle here, say it's a plate. And then we have link 4, which is link BD. All right? Does it make sense? So if we impress an omega 2, 1, which is omega 2 with respect to 1, okay, so that's the omega, the angular velocity of link 2. With respect to 1, it doesn't say which direction, so I'll take it as positive in this direction here. Or do we have some direction? It doesn't look like we have any direction assigned. So I'll take this as counterclockwise, omega 2, 1. I also know that this is accelerating, this is decelerating. So omega 2, 1 is this, and omega dot 2, 1 is this. It's just opposite. Now I don't need omega dot for the velocity diagram, but let me draw it anyway. So we know these have values. Omega 2, 1 is 1 radian per second, and omega dot 2, 1 is minus 1 radian per second squared. So that means that at the next instant of time, this link will be here, and it would have a smaller velocity. Okay, because what we have is that, yes, it's still going in that direction, but it's decelerating. Okay. Velocities tell you where do points go in the next instant of time. Accelerations tell you how velocities change in the next instant of time. Okay, don't be fooled by the fact that the acceleration is that way that doesn't mean that the link is moving clockwise. The link is moving counterclockwise because that's a prescription by the velocity always. Okay, so let's analyze what's the velocity of point A. Now, what you do is always you want to find the velocity of all points. So the velocity diagram is a graphical representation of the velocity vectors of all points of this mechanism. That's the idea. That's what a diagram is. So velocity of O, well, the velocity of O is a point because the velocity of O is 0. So there is no vector. So let's start with O. Now I'm saying I'm going to start here and I have O and D because O and D, they have the same speed, which is 0 because they are both fixed. And again, I have the luxury here of using this digital thing so I can start wherever I want. And if I don't like it, I can move it around or scale it up and down as much as I want. If you do it on paper, you choose a scale factor so that the largest vector fits in your paper. If you don't know your largest vector, you have to be a bit like you can sketch it first and see where to start from. Okay, and then you do it. Or you do it twice. The first time is the unlucky try, and then the second one you do it correctly. Because once you've done it, it's just a matter of redrawing it better. Okay, so that's how we have always done this. Okay, and that's how the engineers always do this. So please. Okay, what's the velocity of A? Help me out. Velocity of A. Let's look at the equation. Velocity of A, let me write it down here. Velocity of A is, looking at the equation, velocity of A is the velocity of a reference point, which is O, because it's fixed and it's attached to A, plus the velocity of body 2, because that's what connects body A and body, point A and point O, times the distance AO. This is a vector, this is a vector, this is a vector. Do you agree with me? These are just, the vector VA is the sum of two vectors. VO, that means we start from O, we start from this point. So this is 0. And then this vector here is also called, if you want, VAO, which is the velocity of A with respect to O. And what's the direction of that vector? It's perpendicular to both omega 21 and RAO. Now, RAO is this vector. And omega 21 is a vector that is pointing outside of the paper. So you place your fingers outside of the paper, put them onto AO, and find out that the velocity is in this direction. Agreed? Try and do this. So this is VAO. And so that means I have to draw a vector that is in this direction. Now, how am I doing this? If I was on paper, I would take my square set and I'll draw a perpendicular line. And then I'll just use my square set to transport. Do you know how to use a square set? I hope so. No, really. So you should be able to transport. Okay, I'm going to show you.
You do it properly on the exam?
Yeah, I mean, if you want, of course. That's if you want full marks, of course. Again, I'm not sure. I'm not the module leader. So please liaise with the module leader to understand what's required for this kind of questions at the exam. Okay, because I'm sure they will not ask you to do this properly on paper. They will ask you to do something similar or close to. Okay, so what I would do that is I'll draw this and I'll transport this over to here and say this is my VA. Okay, how long is this? Do we know the length? Yes, because we know omega 21 and we know the distance RAO. I know it because it's given. RAO, again, we have complete information of these things, although it doesn't look like. let's say that this is 100. This is 100 millimeters. This looks like 80, something like this. Yeah, looks like 80, more or less. Yes.
How do you this material?
You measure it.
Oh, you measure. Oh,
Yeah. Because it's to scale.
oh, it's to scale. Okay.
Now, I'm not measuring it, but I'm saying that this is 80 millimeters. Okay. So if this is 80, how you do it is this vector here is just, this is 1 radian per second. This is 80 millimeters. And so you have that your velocity of A is just equal to 80 millimeters per second. Agreed? That's which direction? We said perpendicular to both this and this. So that means it's in this direction. All right? So now you draw an 80 millimeter long. Let's say that the scale factor is 1 millimeter is 1 millimeter per second. So you draw an 80 millimeter vector in this direction. And you say that this is VA. VAO. And so if this is VA, this is point A. Okay? I'm calling this VA because VAO is also equal to VA. Okay? That's why, because O is fixed. Okay, now let's check the velocity of B. Let me check the chat as well, because it's flashing chat, flashing. Yes. Okay. So what's the velocity of B? Let's use the Grail, okay? Do you know about Santini? You probably don't know about Santini. It's a very Italian thing. Santini are small pictures of saints. Okay, small saint mean. Santino means small saint. These are small pictures of saints that religious people in Italy bring in their wallet with them all the time. Okay, so this is your Santino. Okay, so you put this in your wallet and you never let go. Okay, because this is all you need. Okay? You print it out, put it in your wallet, and you look at it when you want some comfort. Okay, so let's use the same equation again, but let's now look at point B. Now, which point would you say is the best reference point for B? Because again, you can write this equation with respect to all possible reference points. So VB equals V, which reference point?
D, the last one.
Okay, let's use D, plus omega for 1, so the angular velocity of that body, vector RBD. Okay, I am using exactly the same equation, just changing the subscripts. Now, what do we know about VD? Well, VD is fixed, VD is 0, because we know we start from here. This is D. So this is a very good choice of reference. And what else do we know? Do we know RBD? Yes, RBD is given. Well, it's given, not given. Let's say it's let's say this is 100 millimeters because I measured it. Okay, so we know that this is 100 millimeters. Do we know omega for 1?
No.
No, we don't. We don't. So are we stuck?
No, we can just create an infinite line and derive
Exactly.
line.
So the only thing that we don't know is the length. What we do know is its direction. The direction is now. We don't know how long is the vector, but we know it must be perpendicular to this one and this one. Now, this one, it's either pointing out of the paper or in the paper. So we don't care because that means that the resulting vector is in the paper. So this one only tells us the resulting vector is inside the plane, so we can draw it. We don't need a 3D thing. And so the important information here is that this thing is perpendicular to RBD. Okay? And that's the only thing we know. We know it's perpendicular, and that's it. So we start from D, because this is our reference point. So we start from this point here. And we say that, so let me also remove all these things. We start from D, and we say that, okay, let's take this as my perpendicular vector. Let's see. Let's make it as perpendicular as we want, as we can. So this is the direction. And that's it. You only know that it's in this direction. That's all you can say using that equation. Okay, are we stuck? Well, this is a dead end, but we got one bit of information. If we could get one more bit of information from somewhere else, that would be great. Now, what do we know? We know VA. So can we write the equation of the velocity VB with respect to A? Yes, of course we can. We just use the Santini all over again. Just use the Santino. You get that VB, the same VB, so the same vector is this thing, but it's also the velocity of A plus what? Which omega? What is the body connecting A and B? It's body 3. So it's omega 3 1 now. Vector RBA. Agreed? Exactly the same velocity. Okay, do we know VA? Yes, we do know VA. So we start from VA, we start from A, and we draw a line that is perpendicular to BA, because we don't know anything. We know that omega 3 1 is unknown. But we know that it's pointing outside or inside of the paper. So the resulting vector is in the paper, because it must be perpendicular to it. All right, so if I do this, I get that, let's say that RBA is 110, 120 millimeters. Okay, I'm inventing here, okay? I'm not measuring it. But I need it for calculations later. So what do? I draw a line. So let's call this line here, I want to call it the B line, because point B will lie on this line, okay? Point B will be somewhere along this line. If we knew that the velocity of B was this, then B is here, okay? If you knew that the velocity of B is this, then B would be here, okay? Probably we don't know where B is. Now this is B line with respect to D. And now we can draw the B line with respect to A. But this line will intersect at some point, and that point is B, because B must lie on both lines at the same time. And there is only one intersection point, so that must be B. So let's draw the B line, this line perpendicular to this AB link. Let's say this is 90 degrees. Let's say this is 90 degrees, okay? And we attach this to A. We must attach this to A, okay? Because we start from A. Let me show you. So first of all, let me call this B line with respect to A, because VB is VA plus this vector here. And so VB is VA plus this vector here. See what I'm doing? And VB, so the same vector, is also VD plus this vector here. So VD is 0 plus this vector here. Okay? See what I'm going? I'm going to B. This point must be B. And so I can say that this vector here, I can call this vector here, I call it VBA, velocity of B with respect to A. And this vector here, I call it velocity of B, which is also the velocity of B with respect to D. You agree with me? Because VD is 0, so VB is VBD. Can you show you got the B line with respect to D again? Of course. Why omega 3.1 and not omega 3.2? So first of all, omega 3.1 means how the body, this plate 3 is moving, is rotating in plane with respect to the ground. So it's the absolute angular velocity of 3. So it's always 3.1. You also call it just omega 3. Everything that has a 1 attached at the end means absolute. It's just a way to make sure that we are on the same page, because see, omega 3.2, this omega 3.2 is omega 3 minus omega 2, exactly as VBA is VB minus VA. All right? Omega 3.1 is omega 3 minus omega 1, but omega 1 is always 0 because it's fixed. It's the omega of the ground. So that's what it is. Okay, so this looks horrible because it's tiny. You can make a much better job than me, okay? And also to scale. But yeah, so that's it. We found VA, VB. Do we need C? Yeah, let's do C. I mean, I don't think we need C, because once you know what A is doing and B is doing, well, C is very easy. But again, for the sake of completeness, let's find VC. How do you find VC? You choose a reference point. Which reference point? Well, we now know VA and VB. VA is the absolute velocity of A. VB is the absolute velocity of B. And both points are also connected to C. So I take the first equation with respect to B and the second equation with respect to A, and I find what's happening to C. So I find a C line with respect to A, a C line with respect to B, where they intersect, that's point C. And then we check. So I'll go here and say VC is VA plus which omega? Which omega? Omega what? 3.1. Because we are still on body 3. Okay. Okay, so what is this? Well, this is VA, so that means I start from VA and I draw a line, this line, so this is V. Let me call this with this name. This one is also called VDB, sorry, VBD, V of B with respect to D. This one is also called VBA. So this one is called VCA. So velocity of C with respect to A. That means I must start from A, I start drawing it from VA. So I start from VA, and let's do it this orange now. And I draw a line that is perpendicular to CA. Perpendicular to CA is this one. As perpendicular as I can make it. And I must attach it to here to A, point A. And this is my A line, sorry, C line with respect to A. Now I do a line with respect to B, but I have to draw the other equation first. VC is also equal to VB plus still omega 3.1, because that's the same body. They are on RBC, sorry, RCB. And so this is also called VCB. And we know that this vector here is perpendicular to RCB. So RCB is this, so perpendicular to this is this vector, this direction here, as perpendicular as I can make it, must pass through B. Okay, it must pass through B because I start from B. This is VCB, VC with respect to B. So I start from B, and this is my C line. This is my C line. With respect to B. And where do they intersect? Or the C line is called the C line because C must lie on that line. But we have two C lines, so C must lie at the same time on both lines. So that means it can only lie here. So this is point C. And so that means that this is the vector VCA, this one. This one is VCA. This one, see, that's getting very messy, sorry. This one is VCB. And what's VC? Is there VC anywhere?
Yeah.
Where is it?
On the graph is well from B to C and then the pictures on the bottom.
Yeah, so it's not one vector. You see what I'm saying? Let me copy this. What I'm saying is that VC is VA plus VCA, so it's VA plus VCA, or VB plus VCB, VB plus VCB. Okay? But the vector itself, I have not drawn yet. The vector I need is this one. Agreed? Because that's the sum. That's the sum of those two. Okay? So this one is VC. Okay. Okay? I mean, it's horrible. I give you that. But we can make it larger. I mean, I can just scale it up very easily. Still looks horrible, but larger. Okay? Good? Any questions? No? I mean, it's not hard. It's just always the same thing. Literally always the same thing. You just have to make sure what's going on and how you solve these things.
Sir,
Yes?
how do you find the directions?
The direction is, it comes from here. See, it's always perpendicular to, this means in plane, means in the paper, and perpendicular to this. So this is what gives you the direction. Once you know BC, is this, you know that VBC, which is, sorry, VCB, this one is just perpendicular to this. Okay?
Okay.
So everything CA is perpendicular to AC. Okay?
Okay.
And that's so on and so forth. They're always perpendicular because that's how the definition works. All right, you don't have any questions, but I want to show you, before I give you a break, a well-deserved break, I want to show you how do you treat these kind of problems. Because look at this. Here we have a sleeve, say, and a piston in a sleeve. So how do you do about that? So let's do the velocity diagram of this other thing. So you can do these by yourselves, because then we have to do the acceleration diagrams now. So let's do the acceleration diagram of this. We take this down. We know that, we have all the information here, okay? These are all given. So now this is much better. And we want to find what happens to 2, 3, 4, and 5, and A, B, C, D, E. Okay? Oh, one thing that I didn't tell you is now that we have these vectors, we can find all the omegas. So you remember that the omegas were all unknown. Now that we have VCB, we know that VCB is omega 3 times RCB. This we can measure here. This we have measured earlier, so we can find omega 3,1. So you can say that omega 3,1 is VCB divided by RCB. Agreed? Huh? And omega 4,1 is here, look. So it's VBD divided by RBD. VBD divided by RBD. And of course, I'm saying these because these are the magnitudes of these two vectors. The magnitude of VBD divided by the magnitude of RBD. Agreed? That's it. So you have all the information. You can measure all the velocities of all points and all the angular velocities of all bodies. That means you have complete information. You need these angular velocities because when we do the acceleration diagrams, they are required to find the accelerations. Remember, what is the centripetal acceleration? Omega squared times r. So omega squared, that means that you need omega 3 and omega 4. So you need to do the acceleration diagram, you necessarily need the velocity diagram first. Okay, let's do this very briefly. So what is the velocity of A? Let's say that omega 2,1 is given. I don't know which one is given here, but let's say that omega 2,1 is given. And let's say it's going in this direction. So what's the velocity of A? The velocity of A is the velocity of O plus omega 2,1 vector RAO. Always this. Always, always, always this. Velocity of O is 0. And that means that the velocity of A must be perpendicular to AO. So that means it's in this direction. Okay, this is VAO, which is also VA. How long is it? I don't know. So let's find out, because we know that omega 2,1, let's say, is 1 radian per second, and RAO is 100 millimeters. It says here, but this is 100 millimeters, so the velocity is 100 millimeters per second. Agreed? So we can draw a vector that is 100 millimeters long. This is 10 centimeters, probably too large, so I would use a different scale factor. And it's in this direction. So let's say I'll start from this point. And this point is O and C. O, C, because O is fixed and C is fixed. And then I draw this one, which I'm saying it's perpendicular to this. And this is point A, and this is VAO, which is also VA. All right, that's it. Very easy. Let me check the chat. Yeah, Ravi, it's given. It's given. It should be given. You need at least one velocity, otherwise you can't solve it. This is a mechanism. Mechanisms are 1 degree of freedom. 1 degree of freedom means that when you set a velocity, you know every other velocity. When you set a coordinate, you know all the other coordinates. Okay, I'm saying that omega 2,1 is equal to 1. It doesn't say so, but probably because I just cut out.
That's at the top, right? Velocity.
No, that's the velocity scale. That's the velocity scale diagram. It's the suggested scale for the velocity diagram. Okay. So yeah, unfortunately, we don't know that, but it doesn't matter. Okay. So how do we find the velocity of B? Again, write the equation. The velocity of B is the velocity of, where do we start from? Well, B is here, so it's connected to A, or which we know we have full information, and it's connected to C, which is fixed. So we can definitely say that the velocity of B is the velocity of A plus this down. Velocity of A plus, let me put this here. omega 31 vector RBA. And I can also say that the velocity of B is equal to the velocity of C plus omega 41 vector RCB, BC. Agreed? Exactly the same thing. Sorry, guys, I am left-handed, so when I'm on the far left of the screen, my hand, it's very hard to write properly. Okay? Okay, so that means that I can draw a B line with respect to A. So starting from A, I draw a B line that is perpendicular to BA. That means horizontal. That's easy. So an horizontal line that passes through A. This is my B line. With respect to A. And with respect to with respect to C, this is 0, and I have to draw a line. So I start from C, which is 0, of course, here, it's the same as O. And I must draw a line that is perpendicular to BC. Perpendicular to BC means vertical line that's passing through this point. And of course, this is in the way. So this one is the C line it's not the B line, it's the B line, not the C line. So the line where point B lies with respect to C. So since these are both B lines, so B must lie on these two lines, that means B is here. This is B. So since B is here, that means that this is VB. This vector is VBC, which is also VB. And this vector here, what's this vector here? Look, it's very easy. It's VBA because there's the point in B and the tail in A. VBA. So that means that VB is equal to VA plus VBA. This is exactly what we did. Huh? Great. It works. Let me do this. Okay, now let's do D. So what's point D? Well, point D is exactly the same. Now that we know A and B, we can find point D with respect to A and with respect to B, because they are on the same body. So VD is VA plus omega 3, 1 RDA, and VD is VB plus omega 3, 1 RB dB. There you go. And so this one is perpendicular to DA. That means horizontal passing through A. So again, this is also the D line. This is also the D line with respect to A. They have the B line and the D line with respect to A are the same because they are on the same body on the same distance. Just one is longer, one is shorter. So that means it's the same vector, but one will be half as much or twice as much. And with respect to B, we have so we start from here and with respect to, oh, yeah, we can't do this. We can't do this, see, because what happens that both lines lie on the same thing. So this is one of the instances where you can't, we have chosen two wrong reference points. And this is not the end of the world. But what we can do very easily is observe that RDA so we can observe that this is the velocity of A. This is the velocity with respect to B. Sorry, no, this is the link AD, AO. This is the link AD. So all velocities will have a circle, will do a circle around this. So this, then you have this is VB, and so you have this. This is VD, okay? That's the idea. Or, well, this is just a graphical way of doing it, or you can find the velocity of E first. What's the velocity of E? We know that it's the absolute velocity of E is horizontal. Yeah, there is no way. So what do these lines represent? So this is where this is the perpendicular to the velocity of A and the perpendicular to the velocity of B. So where they intersect, this is called instantaneous center of rotation. I don't know if you did you do this? No. Okay, it's fine. You don't need to know. You just know these by reference points. But for more complex bodies, when you know the velocities of 2 points, you can draw the perpendicular to the velocities of those points, and you find the center of instantaneous rotation. That one is the center around which the entire body rotates. So everything is rotating around that point. So all this body here, body 3, is rotating around this point. Okay, so that's the idea. Okay, so let's find VD. Again, we said that VA and VB are not useful, but what we can say is that VD will be half as much as VB. It must be. So let me get rid of these, otherwise confusing. So we know that VD must be half as much as VB. We use A and B, but we can use A and C. We can also use A and C. We see, sorry, we see. No, we can't use VC because otherwise we don't have it. We don't have one of these. Okay, so we just have to say that since VAB, VAB is this, VBA is this, that means that VDA is half of this. Okay? VBA is this. Imagine that this is point of rotation of A. B moves in this direction with respect to A only. And so that means that D must move in this direction because they must lie on the same line. Okay? So if VB is 10, VD is 5 because it's halfway through. Okay? It's linear. That's the idea. So what we want to do is say that you take VBA and you say that D lies here. Sorry, VDA is this point here. This vector, exactly half as much, is VDA. And so how much is VD? Well, VD is just VDA plus. So this is VDA. And so VD is VA plus VDA, and that means that VD is this vector. And sorry, guys, this is getting messier and messier, of course, because of course it is. There you go. This one is VD, which is VA plus VDA. Okay, VA plus VDA. This is VD. All right. Now that we found VD, so this means that this point is D. So let me get rid of this, put it here. This point here is also point D. And we can now go and find E. E is, of course, horizontal. That's one information that we know for sure, 100%, is that E must lie on this line with respect to O. With respect to O means with respect to the fixed point, with respect to the ground, this E moves horizontally. So this is the E line with respect to O, which is with respect to the ground. That's what it means. This. Oops. And we know that given VD, D and E are, let me write the equation, VE is VD plus omega 5, 1, vector RED. And so that means this is perpendicular to RED. So I start from D and I draw a perpendicular line, which is a vertical line. Which is a vertical line, come on. There you go. Vertical line passing through B. And this is also the E line. This is the E line with respect to D. So that means that point E is this one. And so that means that this is VE. This one is VE. And this one, which I will not draw, but this one here is VED. Okay? That's it. I mean, I know it might be a lot to take in, but it's always easy unless 3 points are aligned. Because if you have 3 points aligned, then the reference system points doesn't really work. And you have to make sure that you understand what's the ratio when 3 points are aligned. If they are aligned in this way, where this is exactly in the middle, then whatever velocity you have here, half as much you have here. But if this was, say, 2/3 of the way, then this would be 2/3 of the speed. Okay? It's just a very particular case. I don't think it will come up at the exam, because we tend to make exams solvable in an easy way. Okay? Don't be scared though. It's just when you have 3 point aligned, it's always like that. It can't be any different. Okay, good. I'll give you a break. 5 minutes though, because we have a lot to go through for the acceleration diagram. Yes.
Could you please go over how you found VE again?
Sorry, second.
Could you please go over how we find VE again?
VE, yes. So the direction is clockwise because I decided so. It wasn't given, so I told you that the direction is clockwise. So how do we find VE? Well, we know that point E, with respect to the ground, can only go horizontally, okay? Because it's constrained to move horizontally. So with respect to O, which is the ground, because it doesn't move, this is an horizontal line, okay? Then with respect to D, VE can also be written as an equation with respect to D. So that's VD, so I start from this point, because this is point D, plus this vector here, and this vector here is exactly a vector perpendicular to ED. Perpendicular to ED means vertical. Okay? And so vertical line passing through D intersects the horizontal line passing through O, and this is point E. All right? Yes, see, in the exam, you must be given at least one velocity. Yes.
You know the whole reference system that you do. Yeah, I don't really understand.
The reference point can be any point.
Well, like, you know how you said that you like drew 3 lines and like there was a point there. I don't really understand why.
No, that was just, it was something that wasn't explained. It's called the center of instantaneous rotation. Okay, you didn't do that, so I don't worry about it.
Sorry? Sorry?
Oh, yeah.
You write cross product as half an x. I guess that's accidental, right?
Cross product as?
Half an x.
What do you mean?
I mean, it just looks like half of an x, like the bottom half.
It's this. I mean, it's another way of drawing the cross product. It's either this or this. It's the same thing. I mean, it depends on how you.
Isn't the lower one in vector algebra and it means something a bit different?
No, they mean exactly the same thing. It depends on the notation that you're using.
Okay, because I know that the
The
bottom
cross,
one.
I don't like the cross because it looks like an X, and it's
Oh, okay.
it can be confusing. Lynn, how's it going?
Hi,
With us?
another.
Yes, you are.
It's very slow. I want to open the
Now it's
video. Ah, how are you? How was your weekend?
it's fine. I mean, I was expecting an easier time, an easier time when doing these questions on the tablet. It's not that easy. It's much easier on paper. That's what you do. Could you repeat how you got point D? So I got a question here. So yes,
Yeah.
let me repeat how I got point D. So you know that point D, what we have is point D is in between, is halfway through A and B. Okay? Well, apparently no. Yes, it is halfway through A and B. Okay? So what we want, what we say is that once I found this VBA, look, this is the velocity of B with respect to A is this one. This vector here represents VB with respect to A. So since A is my fixed point, I say fixed because it's with respect to A, so assumed as if it was fixed. That means that all the points on this link, all points on this link must have a velocity perpendicular to A, perpendicular to the link. Agreed? And so I am just selecting this one, which is the one I want. And this one here, which is VDA, since this is 130 and this is 65, that means that VDA is half as much as VBA. Agreed? And so that also means that I can go here and say that on VBA, VDA is just the same vector, but scaled down by a half. And so that means now that if I look at the equation VDA, VD is VA plus VDA. So VD, this vector here, is equal to this vector plus this vector. So I find VD. Okay? Let me check the chart. Is this clear? Why does VD starts from OC? Because VD is the absolute velocity of D. VD is the absolute velocity of point D with respect to the ground. Now, the grounded points are O and C. These are ground. Okay? So everything that starts from here, is an absolute velocity. In fact, you have VB going from O to B, you get VB. From O to A, you get VA. From O to D, you get VD. Okay? It's the 0 point because they are both fixed. O and C are both points that are fixed to 1, fixed to the ground. Is this clear? For that, what do you mean that? This omega to 1? I just said it's 1. No, this should be given. This should be given. Okay? What do you mean it's not parallel? Not parallel to what? What is not parallel? Which vector is not parallel to the picture? VD, but it must not be parallel. VA is this, VD is more inclined, and VB is vertical. Okay, so this is VA, this is VD, this is VB. So if I draw this link at the next instant of time, okay. Agreed? Okay, let's resume. Let's resume very briefly. Very briefly, let's do accelerations. Let's go back to this thing. Where you have point P, and this is the, at the next instant of time, you have another P prime. Okay, so the velocity is in this direction. Omega 2, let's say omega. And let's say that the acceleration is in this direction as well. Omega dot. How do we find the acceleration? What is acceleration? Is the derivative of the velocity. You agree with me? So let's remember what was the velocity. Velocity of P is the velocity of O plus omega vector RPO. Okay, looks easy enough. So if I take the velocity, the derivative of Vp, so the acceleration of P is equal to the derivative of P, of derivative of the velocity of p. Acceleration of p is equal to the derivative of the velocity of p with respect to time. And so this means the derivative of the velocity of O with respect to time plus the derivative of this beast with respect to time. Okay, agreed? Now, this is acceleration of p. This one is AP. Okay, now as you said here, it's equal, so of course it is. Equals, what is this? The acceleration of O. Acceleration of O. So it's the acceleration of a reference point plus, what is this? What is this? This is a product. What is the derivative of a product? Come on. The derivative of the first term times the second term plus the derivative, plus the first term times the derivative of the second term. Agreed? Agreed. So we are not done yet. This one is omega dot. So let's call this AP equals AO plus omega dot times RPO. These are all vectors. Plus omega times, what is this?
0.
Why 0?
No, it's R.
That's the velocity of P.
Oh.
That's the derivative of the displacement, RPO. RPO is the position vector. Derivative of the position is the speed. Agreed? So remember RPO, we did this here, all the way back. The derivative R in the t is omega times R. Okay? So if you look here, this is also omega times R. And lo and behold, this is the final formula. As you can see, we don't have 2 terms now. We have 3 terms for acceleration. 3 terms. Ah, ouch. How do we make sense of what's going on here? Well, here, this is easy. Let's rewrite this in this way. Acceleration of P equals acceleration of O plus this term first, omega, cross omega, cross RP, O, plus omega dot RPO. Now this term is what we call tangential acceleration. This one is called acceleration tangential P. And this one is what we call normal acceleration or centripetal acceleration, acceleration normal. P. How do I know that these are tangential and normal? Well, let's look at their direction. We know that this is a cross product between a vector that is perpendicular to the board, and that means the resulting vector ATP is a vector inside the plane, and it's also perpendicular to RPO. So perpendicular to RPO means that AT is this. Let me get rid of this. AT of P is this vector. Okay, it must be perpendicular to PO. Agreed? This is PO. It must be perpendicular. And it's, see, it follows, it doesn't follow omega, it follows omega dot. Okay, so if omega dot is in this direction, then ATP is in this direction. If omega dot was in the other direction, ATP would be in this direction. Okay, so the ruling, the king here is omega dot in this term. angular acceleration, radians per second squared. What about this? What's the direction of this? Well, this is a double cross product. That means perpendicular to the perpendicular. What is perpendicular to the perpendicular? It's just parallel with extra steps. Okay, that's what it is. Huh? It's parallel, but it's not as parallel. Well, it is parallel, of course, the same direction, but it's in the opposite direction. Why? Because let's have a look. These are my two vectors. This is my original RPO. The first cross product gives me this, and the second cross product gives me this. Okay, so perpendicular, perpendicular again. So it's parallel, but in the opposite direction. Agreed? Very important. So it's not in the same direction RPO, it's in the opposite direction. It's ROP. And that means that the centripetal, it's called centripetal acceleration because it's in this direction. Agreed? So it doesn't go in that way, because it goes in the other way. Acceleration normal P. Okay? That's it. That's it. What is the acceleration of P? It's the sum of these two. Well, of these three, because if you also have an acceleration of O, you must also sum the acceleration of O. So the acceleration of P with respect to O is this one. This one, APO. Agreed? Just two components of the same vector. And this one, in fact, let's call this APO. So AP is just AO plus APO. It's the same thing. The relative acceleration is AP minus AO. That's what I'm saying. But AP minus AO has a full story inside it. All right? Let's crack it on. Now, this is the new Santino that we should use. This is what you need to use every time. Put this in your wallet. Oh, apologies. Just crashed on me. Yes. Say again?
Go back to the diagram.
Yep. Yes. What happens if you're going at constant angular speed? That means you have no angular acceleration. Okay. What happens if you have no angular acceleration? This thing that depends on omega dot disappears. Okay, so the acceleration of P is just the normal acceleration of P. Acceleration of P, this goes away, but this does not go away. That does not go away. This depends on omega, not omega dot. Okay, that's why I was saying the acceleration, the velocity diagram is required for the acceleration diagram. Otherwise, you lose all this information here. Do you remember when we said that in first year, we said that the normal acceleration is omega squared r? So omega squared r, see, there you go. Now you have a vector representation of that thing. In fact, the magnitude of this vector is omega squared r. But now this also encodes the direction. So this is more general. It's a more general representation. Remember when we said in first year that the tangential acceleration is alpha r, alpha times r. There you go. That's it. It's here. So it's nothing new. It's something that you have encountered already. This is now a more general form of what you should already know. Right? Good. So let's solve this one again, but now let's look at the acceleration diagram of this. Acceleration diagram. So the acceleration diagram is given omega 21 dot See, I have omega 21 dot here. It's opposite in direction of omega 21. So that means it goes in the opposite direction. That means we have full information on what's going on to the acceleration of A. What is the acceleration of A? Let me write the Santino again. Acceleration of A is the acceleration of O plus the centripetal acceleration. Which omega? This is omega 21. RAO plus omega 21 dot RAO. Agreed? This one is AT AO. This one is AN AO. All right? Altogether, they give you AAO. Again, don't be scared. It's just labels everywhere. So we remember we found omega 21. Omega 21 was a number. So we know how long is this vector, because we have RAO. RAO is 80 millimeters. And so this one is this many millimeters second squared. And we know omega dot to 1, and we know RAO, so this is also this many millimeters second squared. They're all accelerations, of course. AO is 0. So I start from point this one, OC, and I say that the acceleration of A is one that goes in this direction. So it's the sum of these two, this one plus this. The sum of vectors means one after the other. Okay. So first I draw this vector here, and then I draw this one just after it. So this is ANAO, looks like this. This one is ANAO. And then I must attach a vector here that goes in this direction, ATAO, which of course this must be perpendicular to this. So this is 90 degrees, okay? Because one is normal, one is tangential. So they are like, I don't know how long these are, so I'm not sure if this is the correct thing because we don't have numbers. But let's say it's this. So this is ATAO. And so I can tell you that this one is AA, this one here is the acceleration of A. Because it's the sum of AO, which is 0, plus this, plus this. Yes?
So you know, for the acceleration equation, does that say plus AO plus omega 4 times omega 21 times?
It's omega 21 across omega 21. It's omega 21 all the way.
Oh.
It's always omega 21. Now, this is AA. So how do we find AB? Well, AB, again, we find the B line with respect to A and the B line with respect to... Now, all the centripetal accelerations are given, always. Could you explain how to find the magnitudes of the acceleration vectors again? It's just, you know this, because we found it earlier. If you look at this, we found that omega 21 was given. Omega 3,1 you find from here. Omega 4,1 you find from here as well. So the relative velocities give you the omegas, and the relative accelerations will give you the omega dots. That's the idea. So let's do acceleration of B. The acceleration of B is the acceleration of A plus omega. So B and A share omega 3. So omega 3(1) cross omega 3(1) cross RBA plus omega 3(1) dot cross RBA. What do we know? Well, omega, this one is given. Well, this one we just found. This one we found is this. So we start from this point. Let's call this point A. So let's start from point A, and then we draw another vector here of which we have full information. We know everything because omega 3(1) we found earlier. Okay? And RBA is just a measurement. It's just the distance between B and A. And so this one is also these many millimeters squared, millimeters per second squared. What we don't know is this one, who knows? But we know that must be perpendicular to RBA. So after A, let's draw this one, which is in direction B. So it's in this direction. How do I know? Well, it's B, sorry, it's in the opposite direction, because how do I know? It's parallel to RBA, so it's in this direction for sure. But how do I know which direction it's going? Well, since this is the velocity of B with respect to A, remember, instead of going from A to B, goes from B to A. It's always in the direction of the reference point. Okay, so it's in this direction. So let's draw this. And let's say that this is, or let me move this out of the way. And I say that starts. I say I must start from A. Now I don't know how long is this, so let me make it this long so it's larger. So this vector here, also let me change the color. This vector here is what we call acceleration centripetal BA. Acceleration centripetal BA. And attached to this one, we have the acceleration tangential BA, which is, of course, exactly perpendicular to this vector here. Agreed? So this one is the line. This is the B line with respect to A. Let's find the B line with respect to D. And also, this is not C. This is D. Let's find the B line with respect to D. Acceleration of B equals acceleration of D plus omega 4(1) cross omega 4(1) cross RdB plus omega 4(1) dot cross RdB. Okay. What are those symbols? I'm spelling them out as I tell you. This is AB equals AD plus omega 4(1) cross omega 4(1) cross RdB plus omega 4(1) dot cross RdB. Okay. These ones are acceleration centripetal normal BA, which is this vector here. And this one is ATBA, so this one is unreadable. ATBA is the tangential acceleration BA, which we don't know, but we know it's perpendicular to this A and BA. So This one, again, is a given. This one must be a given. We start from D, so that means we start from this point, and the given vector is this one, okay? Because it's always directed towards the reference point. So I draw this vector here as parallel as I can to this link. There you go. That's very, very unfortunate. Let's say this is parallel to that link. Let's make it longer. This one is a acceleration normal dB. And so that means that, sorry, BD, not BD, BD. So this perpendicular to it, which is this one, this is acceleration normal BD. So this one is acceleration tangential BD, which is perpendicular to this. And that means, of course, always in the middle of the way. Okay, so this one is, of course, the B line with respect to D, and so that means this one is point B. So finally, we say that the acceleration of B, which is this vector here, let me do this in orange, the acceleration of B, which is this vector here that goes from O to B, this vector, AB, is the acceleration of A, this vector, plus the centripetal acceleration of B with respect to A, plus the tangential acceleration, that means this one is the vector I'm looking for. This one is the tangential acceleration BA. Or can also be written as the acceleration of D, which means starts from here, plus the normal acceleration of B with respect to D, plus the tangential acceleration of B with respect to D. So I'm looking at this vector here. This one is ATBD. That's it. That's how you do it. Okay. Again, it's just one step more complicated than the velocities because you have one more vector. Every acceleration has 3 terms instead of 2. So it's always the same thing. You have to learn how to do these things. Now, the last thing that we have to do here is how do we find omega 3 dot, omega 4 dot, because that's what's missing. But let's look. Omega 3 dot is here. Omega 3 1 dot is inside ATBA. So once that ATBA is given, we found it. We found this vector. So we know that omega 3 1 dot, omega 3 1 dot is equal to ATBA in magnitude divided by RBA in magnitude. And omega 4 dot, omega 4 1 dot equals ATBD divided by RBD. Okay? And it's given here. Again, these ones are a certain number of millimeters per second squared. You can measure it because you are doing this to scale. And this is also a certain amount of millimeters per second squared. Okay, any questions? No? If not, I'll do the velocity, the acceleration diagram of this other one very briefly in the same way, this one. And then we can go. Okay. Now, at the exam, I don't think you will be asked to draw both diagrams. They probably ask you for one diagram. So if they give you the structure, the mechanism, which is a simpler one, they can ask you the velocity diagram. If they ask you for the acceleration diagram, it means you are given the velocity diagram. So given a velocity diagram, find the acceleration diagram. But given a velocity diagram means you also have to spend some time finding all the omegas, because the omegas might not be given. How do you find omegas? Remember, it's always the VBA, VCA, VBD, all those ones contain the omega. You can always look at the equation. That's the idea. So let me copy this again and paste this again. You know what? Instead, let me see if I can show you the solutions on Aula, which are already on Aula anyway. So we can go over them for 10 minutes. 50, 35, so many modules.
Is there a way to remove them?
No, there is no way, unfortunately. See, if there was a way, I would have used it. All right, let's go here, which is week 5 tutorial. We have the solutions. See? Oh, this is very, see, this is drawn to scale. See, that's what we are expecting you to do. So let's have a look. We have omega to 1 is in this direction, but that means that VAO is perpendicular to AO and going in this direction. This is also full information because this is given, AO is given, so this vector here you can draw very easily. So you start from OA, this vector here is given. Then you find what happens to B. What happens to B with respect to A and what happens to B with respect to O. With respect to O, we know that B must be horizontal. There is only one possible movement here, which is B horizontal. So that means you draw an horizontal line passing through O. And that's it because you don't know anything else. Okay, so that's the B line with respect to O. This one here is the B line with respect to O. You also have a B line with respect to A. How do you find that? Well, it's omega 3 times RBA, which is this distance here. And so since it's times, means it's perpendicular to BA. You start from A and draw a line that is perpendicular to BA. And so you find this other B line with respect to A. So B must lie here. So you know that from O to B, you have VB, also called VBO. It's the same thing. It's VB is VBO. And from B to A, you have VAB. Well, in this case, you have VBA in the opposite direction. Okay. So the velocity of A plus VBA gives VB. And then you do the same for C. And then you do the same for D. Of course, D is vertical, so it's a vertical line passing through O. And there you go. So D is 12.3 centimeters long, but since you have a scale factor of 10 millimeters, 1 to 10, so 12.3 millimeters are 123 millimeters per second. Okay, that's how you use the scale factor. That's it. Now this is an equilateral triangle, very nice. And these are the equations. I mean, it's just the same thing that we've done all together, but this is drawn on paper and using a set square and using the scale factor, which was advertised on the paper. Let me check if we have this one. Oh, this is the one I solved in class last year. Okay, see, can you recognize my handwriting? Yes, I can. Oh, this one. Let me see. Have we got the have we got the solution? Yes. Oh, there you go. Does it look like mine? I hope so. Yes, it does look like mine. Look at this. Yes, it does look like mine. Okay. Aha. Nice. Huh? Although, even without having any square set on paper, it looks exactly like mine. Well, this is still better though, because it got all the dimensions as well. Because you can measure it. Let's check the acceleration diagram. Woohoo, look at this. That's the acceleration diagram. Let me go to the acceleration diagram of this. So this is what I gathered, and this is what they gathered. So yeah, so what we have here is that acceleration centripetal A, so starts from here, then you have something that goes down and right. So this is one, is this. Point B, where is point B? You can see point B. This is point A prime. Oh, D prime, B prime. This is B. Oh, so this one is this tiny one. So see, the fact that I don't have dimensions made me draw this much larger than it is. It's very tiny. And this one is much smaller than it is. So this triangle here should be much larger than this one. Okay? But it's the same thing. We have exactly the same vectors, just different dimensions. So make sure you practice on how to do this using set square and protractor, or at least practicing on a digital tablet or however you want to do this. And please make sure to contact, well, next time you see Faris, which is next Tuesday? No, next Monday. Next Monday at the online lecture, please ask Faris what will be required from you at the exam for these kind of solutions. Okay. All right. Thank you very much, guys. Does this topic usually come up in the exam? Yes, it does always come up at the exam. So we must assess everything. So here at the university, you have learning objectives, and the programs are tailored on the learning objectives. There is nothing that is not assessed, either in the labs, so with coursework, or with exam. Okay? So there is no way one topic does not come up at the exam. They all come up at the exam. Everything comes up at the exam, because that's the way it is designed. Okay? Any questions online? If not, let me stop recording this. Bye.